Hello grade 12, welcome to my channel. And today I figured let's just have a look at these MCQs that you guys wrote, as I'm always interested in those kinds of questions because they create a few issues. But let us have a look at them and see what we can do about them. Alright, now we're going to just be doing these MCQs alone today. Alright, so I got this paper as shared to me by one of the students and they took pictures literally, so just going to be working with that. So 1.1, we are told here a constant net force. So once you hear that word constant net force, what do we know? We know that the force is directly proportional to acceleration. Okay, maybe let's write it properly. We know that the resultant force is directly proportional to its acceleration. Okay, so that means if the force is constant, and so will the acceleration, right? Right. Now is applied to a block. So this means the block is accelerating. There is a constant acceleration. So that means velocity increases, okay, at the same rate. Okay, that's the idea being projected here. Which one of the following statements is correct? The block will move with a constant velocity. No, it cannot be constant because it is actually increasing at the same rate because of a constant acceleration. So that is incorrect. Constant acceleration, yes, because the resultant force is directly proportional to acceleration. Constantly increasing acceleration, not constantly increasing, but a constant acceleration. Constantly decreasing, again, it's not decreasing. So the answer here is option B. All right, good. So that is B. Now let's look at this one. 1.2 says a crate of mass m is stationary. So that means it has zero acceleration, and that means the resultant force will also be zero. Okay, because these two are directly proportional. Okay, on a plane inclined at an angle theta with the horizontal. So, well, when this is happening, we know that essentially there's a bit of few forces that are acting on the block. Obviously, we've got a force up the incline. If this is not moving down, this is basically frictional force. So it should be static friction, okay? And then we've got a force down the incline. This is going to be FG parallel. FG parallel goes with FG perpendicular. So that would be FG perpendicular. Okay, so we know this one is basically mg, or should we say FG. This is the same as FG cos theta. Okay, and that one is FG sine theta. You should know these off by heart already. And then we will have a normal force directed perpendicular to the surface. Okay, the normal force is of equal magnitude with the FG perpendicular, because this object is not dipping into the surface or is not being lifted off the surface. So now the two forces that are acting horizontally are the ones that are going to be doing work on this box. So now we can already tell that that force should be equal to that. At least, at the very least, they should be equal to not allow this box to slide. Okay. Now, knowing what we can do there, we answer the questions. Which one of the following statements regarding the magnitude, what are we talking about? The magnitude of the frictional force acting on the crate is correct. Okay. Now the magnitude of the frictional force acting on the crate is equal to the component of weight of the crate, which is parallel to the plane. Yes, because for us to have a zero resultant force here, the vertical force is already balanced. So that also means the horizontal forces should be balanced for us to have a resultant force of 0. Okay, great. Now, this frictional force is larger than the component of weight of the crate, which is parallel to the plane. This is also possible, because if you have not overcome friction, but is it really possible? It's possible, because frictional force can be greater, but again, to say greater, just a moment. So basically, is this possible? Well, that's a very good question, but what I understand is that the frictional force at an instant is not really great, but we would have, as the opposing force increases, the friction will increase to its maximum. So instantly it is not really greater, but it can increase depending on whether the opposing forces are able to overcome the maximum friction. So at any point we always have a minimum, unless we are already at the maximum. So this statement is not quite projecting the right information, because this thing is an instant thing. It's not about a constant thing. Okay, I don't know if it makes sense that way, but that would not be quite correct. Okay, we're not quite clear on this. In fact, we are clear. Why am I not even not clear? So we are clear that at the instant we see this, the frictional force should already balance this one, but we may find a situation where when we increase this opposing force, the object still doesn't move. This means friction increased to its maximum. Okay, that is possible, but at a go, it is not at maximum. Or should we say, we would not essentially say it's larger than the opposing force. Now, equal to the component of weight of the crate, which is perpendicular. No, this is just the normal force. We know that it's only the normal force that is equal to Fg perpendicular, not the frictional force. Okay, larger than the component of weight of the crate, which is perpendicular to the plane. Essentially, we know that it's going to be Fg parallel that is greater than Fg perpendicular in this case. Okay, so essentially that is not true. So our best answer here is option A. So we know that for 1.2 we've got A. Okay. All right, so 1.3. What is the story with 1.3? We told you a ball is projected vertically upwards from the edge of a building, and we have a sketch, luckily. So the direction of motion initially is upward. So we can choose up as positive. Okay. Now points P, Q, R, and S represent different positions during the motion of the ball, as shown in the diagram. Okay. All right, but we can see that point R is at the same position as point P, but when the ball is moving in the opposite direction. Okay. Q is the maximum height. So at the maximum height, we know that the velocity there is 0 meters per second. Okay. Now, it says ignore the effects of friction. So what are we trying to do? We're trying to do a closed system, which means only the gravitational force will act here, which we know is a conservative force. Now, between which 2 points will the ball undergo the greatest change? Now, greatest means maximum. Maximum. As you know from maths, when you say the greatest distance, we're talking about maximum. So when will we get the maximum change in kinetic energy? Okay, so Kmax is going to be where? We will see that essentially this should be from the top to the bottom, right? Because in this segment we know that the velocity is 0, so kinetic energy is essentially 0. So Ek there at the top is equal to 0. Ek top is 0. And then Ek bottom is equal to a maximum, meaning the difference is greater. That's what we mean. Because the greatest change, it means it's the difference between the initial kinetic energy minus the, what we call, sorry, the final minus the initial, okay? If you look at this one, we will have still maximum kinetic friction between, say, S and R. But you can see there's a value for R there. So the difference is definitely not going to be as great as the difference would be from S and Q. So obviously, this is just how one thinks of this question. Again, it was projected at a particular velocity at P. So this velocity right here minus that velocity, or this kinetic energy minus that kinetic energy at P, it will be much less than when you are subtracting nothing. Okay, so here we essentially are subtracting nothing. So we'll have the greatest change. So the answer will be Q and S. So this one is our answer. So again, this one you don't need to attempt to eliminate much, but it's a matter of understanding what the question is looking for. But again, you can also focus on the change in Ek being the Ek final minus Ek initial. Right, so the greatest difference here is what will guide our answer. And we can see we get the greatest difference when we take nothing away from the final kinetic energy. But with the other points, except Q, we have some kinetic energy, and so the difference is not going to be the greatest. So that's the understanding. Okay, good. Now a ball is dropped from, 1.3, we're choosing D. So a ball is dropped from height h and strikes the floor with momentum p. Okay, now the ball is dropped from a height, so basically we've got height h and a half of h. Now it says ignore the effects of friction. Again, we are imagining a closed system where there's no external forces. The only force here is a conservative force, which is gravitational force. Which one of the following represents the momentum of the ball when it strikes the floor after being dropped from this height? Okay, now the best way to think about this, it's one of those questions, again, you cannot just sniff the answer in the air. You've got to do some workings. So we know that using our energy principles or even equations of motion, we know that at maximum, remember this is dropped, meaning initial velocity is 0. Okay. So if we're dropping this, it means we can simply say mgh at the top is equal to half mv squared bottom. All right, because the total mechanical energy is conserved in a closed system. Now look at this. The total mechanical energy at the top is effectively mgh because kinetic energy is 0. And at the bottom, the kinetic energy is at maximum because there is no potential energy there. Right, so this is why this is like this. And then we can move on and say this implies that m we can just simply say this is mgh is equal to a half mv times v. Okay. Now we can simply divide by half mv. We divide by half mv. This takes that, and then the m takes the m. Oh, what am I doing? So therefore we can see that the velocity here is going to give us, when we divide by half, it becomes 2gh. Okay, so over v basically. So that's the velocity in the first instance. So which means p, its momentum, is when the mass is multiplied by 2gh over v. That would be the expression for our momentum, which essentially, if you look at it, is the same as m, or 2mgh over v. That's what we have. So these questions are not so straightforward, are they? Let's look at the second scenario. We know that essentially for the second scenario, mgh top is going to be half mv squared bottom. Okay, now we do the same here. mgh is going to be half mv times v. All right, so we do the gymnastics here as well. Oh, by the way, that height is basically halved, so let's sort that one out first. So this is essentially mg times half h is equal to half mv times v, and then we divide by half mv, divide by half mv. That cancels, the m cancels m, the half cancels the half, so we end up with gh over v is equal to the velocity. So this means here we want to find out now the first velocity was given to us like that. What happens to the second velocity? Of course, the momentum here, we will see that the momentum is going to be the mass times gh all over v. So this is the momentum in the second instance. But can you see, we need to know now the relationship between these two. For us to know the relationship between these two, what we want to do, we want to say, look, this kind of momentum, let's say P, gave us essentially in terms of P, because you can see all is in terms of P here. P gave us what? 2 mgh over v. Now, what would be this expression mgh over v? We can make it x. So this question is complex, guys, but maybe it's my approach, I don't know. So we just cross multiply there because we want to represent x in terms of p, essentially. Now when we cross multiply, we're going to move into this space right here. So what we get is that we've got 2 mgh right over v times x is equal to, we multiply there, we get p times v. Right, and then we divide by this 2 mgh over v as a unit. And what we do to the one side, we must do to the other side. 2 mgh over v. So that is what we do. Okay, now I'm running out of space to write. So basically this cancels, and therefore our x is going to be equal to, now this is p times v over 1. When we divide by this, we can easily flip this this is going to be flipped into this manner. We get V over, what is that story there? Mark, koni mistake anyana up. I'm making a mistake. Sorry. There's no PV here. Oh yeah. I am making a mistake, a big mistake here. P multiplies this one. It's going to be P mg h over V, right? Because when you multiply that by P, that's what we get. And essentially, this is wrong right there, which we're going to multiply by this expression now flipped, which is going to be essentially V over 2mgh, which is going to be 2mgh. Great. Now we can see V's cancel, the mg's cancel, the h's cancel. So what do we end up with? We end up with just momentum P. Okay, so that is our answer, which means X is also P. So expressing this in terms of P, we just get P. All right, okay, all right. So that means 1.4. The answer is A. So that is P. You're lying. Oh my God. This is basically over 2. So this is P over 2, which is the same as half of P. So the answer becomes C. I'm sorry, guys. So we're getting C, which is going to be the half of that momentum. All right. So 1.5 says a box moves on a horizontal surface. The diagram below shows all the forces acting on the box. Okay. We've got force Q, P, which is the normal force, by the way. And then we've got R, which is going to be Fg. And then we've got S. Obviously, assuming that this is the force acting at an angle, that should already be something like friction, you know. So we can say this is Fk because probably this is moving, we don't know. You can say Fk or Fs. This should probably be the applied force, but it's just our imagination. So it moves. If it is moving on a horizontal surface, one of these two forces is going to be doing the things. The diagram shows all the forces acting on the box. Which one of the following combinations of forces work on the box? Do work on the box. So forces that are acting parallel to the surface are the only ones that are going to do work. So it has to be forces acting on the box parallel to the surface, because it is moving horizontally. So it's only parallel forces. So essentially, we know that Q will have a component of force, which we can say FQ parallel, because in the X direction, it will be moving in that direction. So essentially, all the vertical forces, since this block is not dipping into the surface or is not being lifted off the surface, it means the perpendicular forces are in balance, because it also has an FQ perpendicular. Okay. So meaning those forces, the normal force plus the FQ perpendicular, are balanced by the weight. So the forces that are probably in balance is these two. Obviously this must be an applied force if it is acting at an angle. So this should be the proposed direction of motion, to the right. Okay. So which one of the following combination of forces do work on the box? It's going to be essentially force Q and S, although Q is acting indirectly through its components. So this one is as good as B, because these others include perpendicular forces, and we know that perpendicular forces do zero work. Okay, now let's go. 1.5 is basically B. 1.6 says, now a train moving at a constant velocity. What is it moving at? Constant velocity. Towards a stationary listener emits sound waves of constant frequency. Obviously, we know that the frequency of the source is going to be less than the frequency of the listener here. Why? Because this is moving towards, so there's more compressions ahead of the train than behind the train. So the listener will hear a much higher frequency than is actually emitted. Which one of the following statements about the sound waves observed by the listener is correct? The observed frequency is higher than the emitted frequency, most definitely, because that is what happens when the source is moving towards a listener. Wavelength is longer than the wavelength. The observed wavelength is longer, not necessarily longer, than the emitted, because should the frequency be higher, it means a shorter wavelength. So it should actually be shorter. And because of that statement longer, this is incorrect. Frequency is lower than the emitted frequency. Okay, the frequency is not lower, but it's actually higher, the observed frequency. And because of the lower statement, that is wrong. The wavelength is equal, can't be equal, unless this is already at the same spot or it's stationary, meaning the source is stationary. So, So our best answer there is A. So 1.6 is A. 1.7 is, so for 1.7 we are told here, refer to the diagram below. We're told here Q and R are small spheres suspended by light insulated strings. Okay, that means conservation of charge applies here. Okay, so this is again creating a closed system, because if we're not insulating this, charge may be lost. Okay. When a negatively charged rod is brought close, what type of a rod is this? It's a negatively charged rod. It's brought close to the sphere Q. Sphere Q is repelled, meaning sphere Q has a negative charge as well. Okay, and when the negatively charged rod is brought close to the sphere R is attracted. So this is suggesting that sphere R should be positive, right? Because opposites attract. Now, which one of the combinations below can be possible if the nature of the charges on spheres, what am I saying? Which one of the following combinations below can be possible for the nature of the charges on spheres Q and R? Obviously, sphere Q has to be negative, so that is a possibility. Not possible, not possible, possible. Now, nature of charge on sphere R, it can't be negative. Not sure about the neutron, and essentially it should be positive, definitely, but I'm not too sure about the neutron. So as we can see here, this possibility is eliminated because we don't really have a proper match. I mean, we know this sphere Q cannot be neutral. So that goes. And it definitely is not positive, so this one also goes. If this one is negative, and we know that sphere R cannot be negative, that one goes. And essentially, this one becomes the only one that we're not too sure, because neutral, we don't know whether it will be attracted or not. But I would go with this one, although I'm not too sure. So here, I have to make a choice, and I don't know. But eliminating these others for certain, because I know with certainty that B cannot have Q as positive. So that's why I'm eliminating. And I definitely know also that C cannot be neutral. Okay, so that is the case. So I'm not too sure about this. You guys double check that one. Now 4 voltmeters V1, V2, and V3 and V4 are connected in a circuit as shown in the diagram below. So we've got V1 across the terminals of the battery, that is the total external voltage, and then we've got V4 again on a segment of the wire, so the potential difference between those 2 points in the wire, and then we've got a switch here. Once you've got a switch and it's opened, it means this V3 is the same as that V3 across the terminals of the battery, because if you expand this circuit, you will have essentially 1, 2, 3. So can you see here we will have points, we will have the resistance R, and as we can see, this is just a voltage across the segment, that is V2. And then this goes all the way to the switch, part of the switch. And then if we expand this side, you will notice that we just have points, we just have the ammeter here. Okay, and then we go on. So the ammeter, we've got that 0 voltage. V4 should read 0 actually, V4. And then if you expand this further, you will notice that we will end up at the switch S. Okay, so can you see this part of the voltmeter? If we draw a voltmeter across these ends, can you see this is the same as the voltmeter across the terminals of the battery, because it encircles that. So V3 is that one. So when you expand this circuit, we literally have that V3 as the same as the V1. Great. Which voltmeter or voltmeters will have the same reading as V1 when the switch is open? Again, can you see when the switch is opened? Because when that switch is closed, then this V3 becomes just across a portion of the circuit, not the terminals. So V2 only? V2 has nothing to do with that. V3 only? Yes. Because when that switch is opened, we can see when you expand, that voltmeter is essentially across the battery, but from just a few distances apart, but it certainly is it's a terminal voltage. V4 only has nothing to do with that, and if they were to ask a reading, it should be 0 there, because the ammeter just offers no resistance essentially. Now V2 and V4, not necessarily, so the answer here is B. So we've got B as our answer. Okay, so let's do 1 point, where's 1.8? Oh, essentially I didn't write. So 1.8 is this electric circuit, so we chose B as well. That is B. So for 1.7, I didn't make the choice because we ended up with that choice, D, for 1.7. Essentially 1.9, what is the story there? It says a split ring commutator. Once you hear that, it has something to do with the DC stuff. Connects the coil to a generator, so that generator should be a DC generator. Okay, to an external circuit. Which one of the combinations below is correct for the magnitude and direction? So we're looking at the magnitude and direction of the induced current in the external circuit. Okay, the magnitude of the induced current is constant. The answer is no. So anything that says constant, no, but we know that it changes from max to minimum, isn't it? Then the induced current, because of that split ring commutator, it ensures that the current is constant. It does not change. So which one ticks the boxes is option C. 1.10. Now light of a suitable frequency is shown on the surface of a metal and electrons are ejected from the metal. Which one of the following is equal to the ratio of the work function to the threshold frequency of the metal? I mean, this one you can just say work function divide by threshold frequency. This comes out as, what is work function is Planck's constant times threshold frequency. We're dividing by threshold frequency, so these two cancel, so we remain with Planck's constant. So that answer is straightforward. So sometimes certain questions you can look at them directly and you move on. So the answer is A, so which gives us A. Okay, yep, that is the story. That is the story. Okay, good. So those are the answers for the MCQs. I hope they are all correct, but I'm a little bit unsure of that 1.7. So that 1.7 is a little challenging, but nonetheless, this is an attempt to give you something. So I hope you've learned something and you can take these ones down whenever you get a chance. Otherwise, I'll see you next time. Bye-bye.